Good morning, everyone. My name is Dan Desjardins, and I was asked a very interesting question. How does DCP integrate with existing workflows? And I'll show that this morning with three increasingly complex demonstrations culminating in my own physics research. So I get to show a little bit of what I think is cool, but also how DCP works. So without further ado, the first thing that a user will have to do is install, obviously, Python if they're going to use the Python version, and Node.js. And in a terminal, they'll pip install DCP. And finally, they'll drop two key store files, one for identity and one for compute credit payment, into a folder called .dcp in their home folder. If you need these key store files, just reach out, dan@distributive.network. But for the audience I'm speaking to directly right now, you already have them. They're attached to the calendar invite. Once that's done, researchers who are their workflows include just Python scripts or Jupyter notebooks or Colabs or what have you, can just use DCP inline. And there's no DevOps, there's no containerization, there's no jump servers. There's no resource allocation competitions. It's just use fire and forget. So in this simplest example, I'm importing DCP and calling dcp.init. That gives access to the symbol DCP that can be used within the rest of the code. So inputs is a list or an array of things. Those things can be anything. As long as this inputs list is iterable, it doesn't matter. Here it's integers 1 through 9, but it can be genomics data sets or image frames or CSV files or lists of hyperparameters or what have you. Then you need, or you don't need, but if your function calls for it, you can specify arguments, which also can be anything, more data sets, training and test data sets, or more numbers or dimensions or things like that. Arguments are going to be common to each individual computation, whereas the inputs will be unique to each computation. And finally, you can write a function. This function is 3 lines, obviously quite trivial. You can write a million lines if you want here, or call other libraries or files to create a pipeline here. But essentially, your function is almost analogous to a program that will execute remotely. This function takes X, which is one of the inputs in the inputs list, along with arguments A and B, which here is 25 and 11. And it's calling a progress. Obviously, that's just a heartbeat signal, and it's returning the product. So quite trivial. This is a job you would never distribute in actuality because of the overhead, which is about 25 seconds. You would compute this locally. But when you have multi-day or multi-hour, multi-day jobs, 25 seconds is nothing. And it's worth distributing those types of workloads. And I'll work up to that. And then all you have to do is the job that you're declaring uses DCP, and this compute.for is basically a parallel for loop. It takes the function you wrote along with the arguments and maps it to each element of the input set. And then this job we're decorating, we're putting it into the UOA compute group. We could put it into more compute groups, or we could delete this line entirely and we'd go to the planetary compute group. And then we're calling job.execute, and this is non-blocking, so you can actually write more code after this to do other things while waiting. And job.wait is blocking, and it returns the results in the same shape as inputs. So in a way, DCP will take your function f and map it to an inputs vector x to return a results vector y. And then the post-processing here is quite simple. We're just printing it. And that's it. There's no, the IT teams that deployed the workers at UOA, I think a week or two ago, they don't have to do anything to support the researchers. They don't have to configure dependencies or environments or anything whatsoever. And the researchers don't have to compete for resource allocation. They just write their code and it runs. And this can be inserted in the middle of their scripts where there's some other pre-processing and post-processing, and it just bursts out the parallel components and then brings them back in and then continues continues on in the script. Okay, what does this look like? I hope everyone can see this. I'll just zoom in. So I'm going to I'm going to run this simplest.py. Now, the way I hooked up this job, which is quite minimal, there are no events. So there's like zero feedback here. It's basically just going to deploy the job from my laptop here in Kingston, Ontario, send it to Alberta, deploys across the computers there, and then when it finishes, all the results are going to basically print on the screen. Um, the way this works is that the first three slices of the workload get released, and then once the first one result returns, the others go out. And that's just to prevent people from deploying, infinite recursive loops that never finish and then basically bombs the network. Anyway, in the time that I was speaking there, the job completed in computers in a totally different province and different time zone in Canada, and I got my results back, and I had paid for them. So U of A workers now have some compute credits that were transferred from my account to theirs, and then they can use those to either cash them out or reallocate them to researchers so that the cycle continues. Okay, stepping up a little bit in complexity. So rather than calling it simplest.py, here's simple.py. It's the same stuff, but I added a few things. Import DCP, dcp.init, same inputs, same arguments. The function here, this is new. I imported a library called NumPy. It's a very obviously popular one, but you can use SciPy, scikit-learn, XGBoost, lightgbm, etc. And then you can use the functions from those scientific computing libraries within these remote programs, if you will. And so here it's quite trivial. We're just taking the square root, but using the NumPy library and returning a result. Same job call where we're mapping the function arguments to each element of the input set. I'm putting it into the UA compute group. And now you can see I'm saying, hey, this job requires NumPy. So when the workers get this job, they know to fetch and configure and initialize NumPy so that when the work function calls import NumPy, it's available. Again, this means that the IT teams don't have to do anything with the workers. It's install the workers and forget. And the researchers basically write whatever code they want, and the workers will configure dynamically with whatever they need to do it. Not shown here is the ability to also include a virtual file system to include files with arbitrary other Python code and whatnot. So it can go beyond just the predefined modules. I added a name and a description, and also not shown is you could add a URL. Actually, I'll just do it for fun. Job.public.url equals, this could be Dan .com slash my physics. So, and just in case I have that, it doesn't exist, but if it did, people running my job could actually go in and visit my project description and get interested in what I'm doing. So it's citizen scientist stuff as well. I'm going to delete that. Okay, and then in the event listers, this is kind of rich. There's a rich set of things you can do. I didn't include any of these. That's why it looked like a black box earlier, where job just got deployed and nothing happened until all the results completed. Here, we'll see the job's life cycle evolve. It will print the states. When the job's accepted by the scheduler, it'll print the ID and let us know that it's waiting for results. If there's no progress, okay, and remember I put a progress call on here, and that's if someone creates while one equals true, like infinite loop that will never halt, you'll get a no progress. So it warns people if they have bad jobs. If there's an error, print it. If I run out of compute credits because my job's too big and I didn't, fill my account full of compute credits or get some from my local U of A administrator, it'll tell me and it'll just sort of slow the job down until I refill it. If the job stops for some reason, let me know. And finally, if as a result comes in, I can print it, but I can do more than that. I can write it to a file or I can even write it to a leaderboard. So if I have like a million simulations I'm performing, and I don't want the results from all a million. I just want the top 100. I can receive each result as they come in, write it to the leaderboard, and then I can avoid writing this at the end so that I don't store all million results, which would take up a lot of disk space or memory. Then you could even use those results to launch other jobs, conditionally or etc. You chain these jobs together. This is all you can do. And then notice here, I put this 007, and it's not a reference to James Bond. What I'm doing is I'm overriding the market rate for compute. So here in simplest, there was nothing. It was just an open close brackets. So it just uses the default. Here, I'm electing to either overbid or underbid. So if my university gives me a bunch of compute credits, I can spend them faster to have a higher percentage of the currently available compute resources so that my job finishes faster. So it's kind of like a built-in auctioning or bidding process for people to get their work done faster or slower, depending on how urgent their workload is or not. And it lets people decide what the urgency is, and it completely avoids the resource allocation competition process or anything else. It's totally self-serve. So I'm going to run this, and you're going to see there's a couple more things here that appear. So this is Python 3 simple.py. So now you can see the state is being printed. The job ID appears and it's telling me it's waiting for the job. So if you have a lot of data that's being uploaded, it'll be stuck on the uploading state for longer. So it just gives people some feedback that stuff's actually happening. And you can see the results are flying back in real time here. The first three happened, and now you can see the rest are flying back. And that's the two-part process I was talking about, estimation followed by running. And I have all my results. Okay, so if everyone isn't bored yet, let's go to a real example. This is my own example, my own research computing in physics, where I'm looking at electromagnetic signals being captured by satellite antenna due to, blah, 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 blah. So same formula, import DCP, dcp.init. My inputs are different frequencies. I want to know at different excitation frequencies what the signal strength is going to be as measured by a satellite in space. So here I'm going from 50 to 300 megahertz. I'm doing 30 computations. That's actually not a lot. I might actually do it I need to do it for 500 actually. And I ran that on Alliance infrastructure and it took 12 hours. I want to do this at UOA and do it in like under 20 minutes. That's what we'll do as the pilot benchmark. Anyway, those are the inputs. My function V voltage you can see it's taking a frequency F as an input. And there's a whole bunch of dimensional, arguments, the size of the satellite and the antennas and all this other stuff. And then in my function, you can see my work function, I'm calling a whole bunch of specialized stuff here. Some mathematical special functions like the modified Bessel functions from the SciPy and the quadrature numerical integration for multidimensional integration, and then some scientific constants and whatever. I won't bore everyone with the math here, but I did the theoretical modeling for this stuff, and I basically wrote out the equations as code. And at the end of all this, here's where you can see that very computationally expensive numerical integration routine being called on 3 dimensions. So these are 3-dimensional numerical integrals. So it's a volume of the antenna basically for all of the elements. And then it returns the sum of the voltages at the end here as a result, and it does this for each frequency. So now you can see how this can take a really long time to compute. Here are all the arguments, the dimensions of the excitation coils and the antenna and everything else. And back to what we know and love. Job equals DCP compute.4. The frequencies are the inputs, then the voltage function and the arguments. I'm telling the workers that they need NumPy and SciPy. I'm putting this into the UA compute group again. I'm calling it antenna voltage. And here, again, don't mind this too much. I did some fancy stuff with the events because earlier I just showed you all the simple events where I'm just printing the raw stuff. But here I'm actually doing things. Here I made a progress bar just because, rather than seeing each result come in, with the full printout here, it'll just show me. It's kind of like TDQM for those who are aware. It'll just, show a percentage completion. And then on result, it will just advance the progress bar. And that's my on result function. It just does that stuff. Of course, tell me errors. Those are useful to know. Here, I'm bidding on this job here. I'm feeling rich. Let's pay like 17 thousandths of a compute credit, which itself is worth $0.0003171. So I'm not breaking the bank here. And then the post processing is I'm plotting the results. Okay, so what does that look like? It's in a different folder. Okay, Python 3, and then that's physics.py. And so now you can see I'm not printing like the ready state stuff, and here's a nice neat little progress bar instead. Jobs deployed, and there we go. So each of these actually take like 4 or 5 minutes. Each slice takes 4 or 5 minutes, and so I'm not gonna talk and waste time for another 4 or 5 minutes. But I mean, this is what we're doing. This is a great benchmarking jobs. It's quite deterministic. We ran this on the Alliance infrastructure. It took 12 hours for 5-minute slices. I'd love to run it at scale on your infrastructure and then show the time difference. And what's great is that the Alliance actually puts a dollar value on CPU years and GPU years. And I've calibrated the price of this job to match those. And so it allows us to show, at Alliance dollar figures, how fast any other infrastructure, whether it's a fridge or a laptop or existing infrastructure, would earn, because some computers and devices will be faster than Alliance infrastructure or slower. And so basically, the economics of compute are baked in through benchmarking. I hope everyone found that interesting, but it's pretty simple in terms of building DCP directly in line with existing scripts and skipping all of the DevOps, Docker container packaging and jump servers and all that other stuff. And IT teams don't have to do anything to support researchers who can basically 100% self-serve and write and deploy code. There's more functionality here than I showed, like routing data, behind the firewall and federated computing across hospitals and all kinds of stuff like that. But I think of, and I don't want to overstay my welcome. So if you're interested in specifics or more sophisticated demos with like genomics or whatnot, happy to demonstrate those. Again, I can be reached at dan@distributive.network. Thank you very much. Have a wonderful day.